So,
I don't hear you anymore.
yes, this talk will be given by Clement Pellegrini, so from University of Toulouse. So over to you.
So thank you for giving me this opportunity to present my work. It's a work in collaboration with Tristan Benoit, who was in India with you a few days ago, and Laurent Bruno from Cergy University in Paris. So I am going to speak about quantum trajectory, which is the main subject of your conference, and a particular physical model, which is called one atom maser. Oh. Sorry. So the plan of my talk will be, first I will give you an introduction of quantum trajectories that you have maybe already seen this week, and then speak about the model of one atom maser. So the main telco of my talk will be a quantum measurement model, quantum trajectories, and I want to focus on the large time behavior of these quantum trajectories, and principally in the infinite dimensional system. So you should have seen this picture many times during your conference. This is the Serge experiment. So you have a cavity, which is C, and you have a beam of atom that interacts with the cavity. And after interaction with the cavity, you perform a measurement, then you have a random result, and you can update the evolution of the cavity conditionally to this result. So it is typically a subfield of open quantum system theory. You have the cavity which interacts with the environment. And this is typically out of equilibrium models. So the basic notation, so my system will be described by a Hilbert space HS. And then on this Hilbert space, I consider the density matrices, which are positive operator, which are Saclay. I am working in infinite dimension, and the trace of this operator is equal to 1. So this is the usual density matrix on the quantum systems. Trace is the trace in infinite dimensional Hilbert space. And the general picture is that this system interacts with a probe, which I call epsilon p. And this probe is equipped with a state, beta. So initially, I have a separate state, rho tensor beta, and then they interact through a unitary operator, U. So U is, as usual, you solve the Schrödinger equation. So during a time tau, you have U is equal to exponential I tau h, where tau is the time of interaction. And then you want to forget the probe, then you trace out of the probe, you take the partial trace on the probe, and then you know that you have a quantum channel, which is called phi. Then this quantum channel describes the interaction with the probe, with HS with the probe, and you can write this under the form of a sum of W of V omega rho V omega star. This is the usual Krauss decomposition. And you have a condition which has to be satisfied, is that the sum of V star V should be equal to identity. And then if you iterate this procedure, then if you put your system with a second probe and then take the interaction, take the partial trace, you have a second stand, which is rho 2, which is just the interaction of phi. And so after time t, you end up with a state which I call rho theta t, and which is phi t, so the iteration up to time t of the initial state rho. And in these pictures, we want to introduce indirect measurements and to have quantum trajectories. Is it okay so far? So if you have any question, do not hesitate to stop me. Okay, so what is an indirect measurement? When you have an indirect measurement, it means that after interaction, you perform a measurement of the probe, and this will give you a random result, which I call omega in a certain state, in a certain set. And you may know that if your initial state is rho, then you get a result omega 1, and which appears with the probability, the trace of v omega 1 rho, v omega 1 star. So this you can find with the Born rules. And when you take the projection postulate, you know that if you have observed the result omega 1, then your state is modified, your initial state is modified, and becomes rho 1. Then that you can describe by the v omega 1 rho, v omega 1 star divided by the trace. So this is the state after the interaction and conditionally to have observed the result omega 1. Then a second copy of the probes interacts with rho 1, and then you get another result, omega 2, and you have a second state, rho 2, which depends of omega 2 and omega 1, and which is just the iteration of what we have just described. So you have your state, which is v omega 2, rho 1, v omega 2 star divided by the trace. And again, you can describe the probability of the occurrence omega 2 and omega 1, which is given by the trace of v omega 2, v omega 1 rho, v omega 1 star, v omega 2 star. So this is the basic description of quantum trajectories. And then you can iterate these procedures, and you have a sequence of measures, and you collect the result of measurements. And then you have a result, which is omega, which is a sequence of results. And after time t, you can describe your state rho t by the product of matrices, which is v omega t, v omega 1. So essentially, it means that you have taken randomly some matrices, and you make this product. And this allows you to describe the evolution of your state. And you can describe rho t just by rho t1, which is v omega t, the results that you have collected at time t, v omega c star divided by the trace. And of course, you can describe the probability of seeing omega t, omega 1, which is given by the formula trace v omega t, v omega 1, rho, v omega 1 star, v omega t star. So essentially, you can describe all the evolution of the state by this product of random matrices, by this random product of matrices. And now, as you can see, rho t can be described just by rho t minus 1. This means that rho t is a Markov chain, and this Markov chain, this is called quantum trajectories, and this is the description of the evolution of a quantum system undergoing indirect measurement. So if you are physicist, you like this description, and if you are a mathematician, maybe you are probabilist, you can say, okay, now I can forget where it comes from, and so I have a Markov chain. What can we do with this Markov chain? So maybe a first property, that what happens if I take the expectation of rho 1. So I have an initial state, which is rho 0. So I have this random evolution, and I want to take the expectation. So the expectation is the sum over the results of rho 1 of omega, and the probability to see rho 1 of omega is the trace of v omega rho 0, v omega star. Then you take the definition of rho 1, which is the v rho 0, v omega star divided by the trace. And so the trace cancel out, and you recover your quantum channel. So the expectation of rho 1 gives you back the quantum channel. And if you take the expectation after time t, you have the evolution of the quantum channel with the iteration up to time t. So what I want to study is the large time behavior. So I can ask first, what is the large time behavior of the deterministic evolution? Without measurement, I want to understand the large time behavior of phi t. essentially, the question is, do we have, for all initial states, a limit of the iteration of the quantum channel? And so if I take the limit of phi t of rho is equal to a certain state, which I call rho invariant, I have that rho invariant is an invariant state of the quantum channel. So, and the state, so it means that if I have started with rho invariant as an initial state, this state is remain stationary. So at any time, phi t of rho invariant is equal to rho invariant. So this is for the deterministic evolution. If I speak about the Markov chain, the things are different, because the notion of invariant state rho invariant is replaced by the notion of invariant measure. So I have a random object. So in long time, I can expect that I have a stationary regime, but this stationary regime will be described by a random measure. Sorry, by a probability measure, and I call it nu invariant. So nu invariant is a probabilities distribution on the set of density matrices, and it means that if rho 0 is distributed along this invariant measure at time 0, then for all t, I have the same distribution. So, and I recall you what are the definitions. So the expectation of f of rho 0 with this probability measure is just the integral with respect to this measure. And what I have said that rho t is distributed along this invariant measure, it means that if I take any observable f, if I take the expectation of f rho 0 is the same as the expectation of f rho t for all t. This is what I called an invariant measure. So if you have any questions, so do not hesitate. So if it is okay, I can go ahead.
It's perfect, Clement.
Sorry?
It is perfect. Continue.
Okay, thank you. So today, I want to focus in infinite dimension, and especially I will speak about the model of one atom maser. So I thought that Tristan, during the first week, speak with you about the large time behavior in finite dimension. And we are able to prove that under two principal conditions, there exists a unit invariant measure, and that in long time, the quantum trajectory reach this stationary regime. So the condition is an ergodicity condition, the uniqueness of invariant state for the quantum channel, and a purification condition. So if you want to understand roughly what is the purification condition, it means that in long time, if you start with a mixed state, and if you perform the quantum trajectories, and I would say in a perfect measurement procedure, then rho t becomes pure in long time. In fact, you can see that the entropy decreases to 0 when t goes to infinity. And then you have a condition to look at if you want to see if purification is true, is that you have this condition that if you take any result of measurement, if you take V star omega 1 product with V star omega t product with V omega t V omega 1, and if you take a projector, if this projector is proportional to the projector, you have purification if and only if this projector is of rank 1. Somehow, if you have a projector of dimension 2 which satisfies this condition, we say that the image of this projector is a dark subspace, and a quantum trajectory, in fact, perform a random walk in long time into this dark subspace. And in this dark subspace, the quantum trajectory is described by unitary transformation. So, and you know that if you have unitary transformation, then the entropy is constant along the trajectories, then you cannot have purification. So what are the problems in infinite dimension? So first, the infinite dimension, you have to understand the ergodicity condition. Does there exist a unique invariant state for the quantum channel? So there is an important literature on this subject. You have many different examples, many very important criterion to show that there exists a unique invariant state. But for the purification condition, as far as we know, there is no criterion. So there is no equivalent of this criterion for in infinite dimension. And you have also other problem. For example, you cannot ensure that there exists an invariant measure. In finite dimension, everything is compact. So you can use fixed point theorem to say that at least there exists a unique invariant measure. But in infinite dimension, this is not ensured. And then you have to tackle this problem. And as I point out, so the main problem is the lack of compactness of the density matrices. We don't have so far a general result like in the finite dimension, but these are work in progress with Tristan, Laurent Bruno, and Martin Frass. So let me explain the model of one atom maser. So the one atom maser is related to the Serge-Haroche experiment. So the systems that I am interested in is the one mode of an electromagnetic fields in a cavity. And the probes are just Rydberg atoms. These are two levels atoms that are going to interact with the electromagnetic field in the cavity, and then you perform measurement after interaction. Okay, so the field of the cavity will be a Fock space, which is the Fock space over C, which we can see as the space of L2 of n. And I have the Hamiltonian of the system, which is given by epsilon, a scalar, and A star A, where A and A star are the creation and annihilation operator on the Fock space. So if you don't know what is A star and A, do not worry. So A star E is the number operator. And when you have the number operator, it acts on the Fock space. And if I have n, n applied in small n, it gives you little n, n. So the Fock state, which are the eigenstate, are the eigenstate of the Hamiltonian. Also, for the two-level atoms, I take the same Hamiltonian, so you can write it as a matrices like that. And you see that if you are in the ground state, minus, it gives you 0. And if you are in the excited state, it gives you epsilon 0, the excited state. Again, you can write it as B star B, and B and B star are the creation and annihilation operator on the two-level system. You put interaction in your two systems, so you take the so-called dipole interaction, which is given by this operator V, which is lambda. Lambda is a constant of the coupling, A tensor B star plus A star tensor B. Then you put everything together, so you have the interacting Hamiltonian, which is at the big H. So it's the interaction of the system plus the interaction of the probe plus the interaction Hamiltonian. And this is called the James-Cummings Hamiltonian. So you take the exponential of this Hamiltonian for a time tau, the duration of the interaction between your system and your probes. And all the state of the probes will be in an equilibrium state. So all the probes, all the two-level system will be at equilibrium, which is given by the Gibbs state, which is given like that. So exponential minus beta h divided by the trace. And again, if you want to compute the quantum channel, you put your interaction and then you trace out of the atoms. So you have a formula like that with 4 Krauss operator that you can totally describe. So what is interesting is to see that there are 4 operators, which is V minus minus, V plus minus, V minus plus, and V plus plus. and you can describe everything. So you take the exponential of your Hamiltonian, you take the expansion in series, and you compute all the quantities that you want, and you have this result. So everything is how to say explicit. And then now you will introduce the aim is to introduce the indirect measurement in this setup. So maybe I should give you some preliminary results. So if my state is in a pure state, in a Fock state, so for example the ket-bra n-1 n-1, v plus minus send you in the state nn, and v minus plus send you nn into n-1 n-1. And v plus and v minus are function of n. So if you are in the Fock state n, you remain in the Fock state n. And if you are in the Fock state n-1, you stay in the Fock state n-1. So as you can see, all the Fock states are stable by this evolution. So there is a non-generic case where in this sinus, the square root of zeta n plus eta is an integer. So this means that the sinus becomes 0. So, but this is called the resonance case. But I won't deal with this case. I will just deal with the non-resonant case. And in this case, there is an interesting result from Laurent Bruno and Claude Alain Pillet, that if you look at only the quantum channel, there exists a unique invariant state, which is given by the Gibbs state, where I recall that epsilon 0 n is the Hamiltonian of the system. So somehow you have a thermalization of your system just by making him interact with the probes. So we don't have a speed of convergence in this case. So now I want to come back to the indirect measurement. So I start with a initial state ρ0, which is equal to rho, and I need to describe how ρ1 is going to be described. And somehow, if I introduce this Markov kernel, which is pi rho or S, it gives you the probability to see ρ1 in S, knowing that initially ρ0 is equal to rho. So it's just a more abstract description of what I have presented. And this Markov operator, it acts on function like that. So Pf of rho is just the expectation of f of ρ1. So you have this sum of f with the quantum trajectory and the probability. And also this Markov operator, it makes the measure evolves. If ρ0 is distributed along nu, then ρ1 is distributed along nu pi, where nu pi is given by this formula. And again, I recall that if I want to have an invariant probability measure, so it means that if ρ0 is distributed along nu invariant, then ρt has the same distribution for all t. But in fact, there is nothing that ensures that such a probability measure exists. In finite dimension, it is always true. In infinite dimension, it's not true. But with Tristan, Laurent Bruno, and Martin Frass, we have found a general criterion for showing that there exists at least one invariant measure. But here, it is useless. In fact, the fact that the Fock states are stable by the evolution. So I recall you that v plus minus 1 send n-1 to a Fock state n, and v minus plus send n decrease to n-1. In fact, if I start with a Fock state, I remain in the Fock state. So I call Fock state all this ket-bra nn. And in fact, you see that under this state, under this fog state, I have a classical birth and death process, and I can describe all the probability to, if I am in n, I go in n-1 with this first probability, n to n+1 with another probability, and I stay in n for this with the remaining probability. So it means that if my initial state is a pure fog state, I remain in a pure fog state, and then I have a classical birth and death process, a classical probability model. This is a Markov chain on n, and this Markov chain has a unique probability measure, a unique invariant probability measure, which is given by this formula. So the probability to be in the state k is given by this quantity, which is just the probability to see that my invariant state, which was the give state, is in the state k. So there is a general criterion for classical birth and death process, which gives you this probability. And then, under this condition, you know that there exists an invariant measure. So what do we know so far? So there exists an invariant measure. So the question is this unique invariant measure unique? And in fact, we will see that everything is related to this classical birth and death process. So the fog state is an attracting invariant state of the Markov chain. And in fact, this will be our purification results. We will see that if we start with an arbitrary state, in long time, I will be attracted by this fog state. And even if I have a mixture of fog state, in long time, I will select one of these fog states. So this is the description. So I don't want to go into the details, but this cylinder algebra, you should keep in mind that it gives you the result of the measurement. All the sequence of the result measurement, you can put them in a sigma algebra, which is called the cylinder algebra. And if I have a result, I can describe this product of random matrices. And my Markov chain is given by WT row, WT star divided by the trace. I can describe the probability of seeing a result. So the probability to see a result W1, WT up to Wn is the sum of all the results in On given by this trace. And we can also describe the combination of the evolution of the quantum trajectories with the result of measurement, which is given by this measure p nu. But what is interesting is that if you want to see what is the second marginal of p nu, so here D is the set of density matrices, so you have an integral of this sum. You can put the integral into this sum, and you recover here the expectation of rho 0 with respect to nu. So in fact, p nu, the second marginal of p nu is just p where you have forgotten what is the initial distribution. You just have to know what is the expectation with respect to this distribution. And this will be very important. So in fact, well, in other words, we can say that if I have a random variable z which depends only on the result of measurement, when I mean which depends on the result of measurement, it means that this random variable is described without description of the quantum trajectories. Then the law of this random variable with respect to nu is just the law with respect to the expectation of the initial state with respect to this measure. So what are the example of random variable which depends only on the result of measurement? Is Wn, for example, the product of random matrices. For example, you can also see at the function which gives you that the result number k is equal to plus minus, for example. Or if you take empirical law, all these random variables are processes that depends only on result of the measurement. And in fact, what we are going to see is that purification, in some sense, means that your quantum trajectory will be closer and closer to a random variable which depends only on result of measurement. In long time, you will forget what happens initially, and this is the spirit of stationary regime. You want to forget what happens initially, and we will see that it will be given by the purification. So if you have some questions so far, do not hesitate. Okay, so let me ask you a first question. So if I take nu, which is an invariant measure, what can I say about the expectation of rho with respect to nu? So I have a density matrix rho nu. What can I say to rho nu? Do you have any ideas with respect? What is the link with this state rho nu with respect to, for example, the quantum channel, the underlying quantum channel? If not, maybe I give you the answer. So remember that the expectation of rho 1, you recover the quantum channel phi of the expectation of rho 0. So now, if nu is an invariant measure, I say that when you take an expectation of rho 1, you have the same expectation of rho 0. The expectation of rho t is the expectation of rho 0 if nu is an invariant measure. If you plug it into the equation, you find that phi of rho nu is equal to rho nu. So it means that rho nu is the invariant state of the quantum channel. So if I take the expectation of an initial state with respect to an invariant measure, I get the invariant state. And in fact, if you see that if I take nu A and nu B two invariant measures, and if I take a process which depends only on the result of measurement, I say that the expectation of f of zt with respect to nu A is the expectation where, in fact, I forget the invariant measure and I take only the expectation of rho with respect to this invariant measure. But this will be equal also with the expectation of nu b of f of zt. So somehow it means that if I look at a process which depends only on the result of the measurement, it has the same law, whatever is the initial measure, as soon as I take the initial measure into the invariant measure. And everything will be given by this process. We introduce this process, and this process empty. If you see WT, I recall you that WT is the product of V omega 1, V omega 2 up to V omega t. So I take W star WT divided by the trace, and I take the sandwich with the square root of the invariant state. And this process, if you look, it depends only on the result of the measurement. So, I never said what is the quantum trajectories here. So this process MT is in fact a martingale. So if you don't know what is a martingale, do not worry. Essentially, what we know, what we have to understand is that it converges towards a random variable n infinity, which is also which depends only on the result of the measurement. and this convergence holds in any in L1 or in probability, whatever you want. And in fact, what we say that this random variable M infinity is in fact a pure state on the Fock state, which is called N infinity. So I run out of time, so I go a bit quickly to the results. And in fact, what we can see is that we have the theorem of purification. So rho t, our quantum trajectory, in long time will be closer and closer to ut n infinity ut star. So rho t will be in long time closer to a Fock state, and this Fock state is not a deterministic Fock state. It will rotate with ut, where ut is a unitary on our state. And in fact, so let me give you this result. So when you look at this martingale, when you look at the convergence of this martingale, you have a condition which has to be ensured, and this gives you this condition. So this probability is knowing that initially I am in the state n. What is the probability to see zeta 1, zeta L? And if these probabilities are different for some L, this is called the purification assumption in this case, and is very related to observability. It means that if I have two states, two initial states n and m, there exists a sequence of measurements that will allow me to distinguish them. So there is no two states which has always the same result of the measurement. If you are a bit aware of what happens for quantum non-demolition theory, this is what happens, but here it's in the infinite time. And then we have the final results, where there exists a unique invariant measure, which is given by the Gibbs measure. And for any initial measure, in long time, the quantum trajectory will converge to this invariant measure. And so few words of conclusion. You can write a law of large number for your quantum trajectories. Also a large deviation principle, but apparently no central limit theorem. And if you look only at the result of the measurement, there is more work. The literature is better, and you have work for example, for Raphael Ackerman, Federico Girotti, Madeleine Gutta, and Martin van Orsen. And for a general criterion, if you give me an infinite quantum trajectories, so the problem is it's much more difficult because of this purification condition. And so this purification you have to verify on concrete models, and this is what we have done for the one atom measure. So thank you for your attention. If you have questions.
Questions?
Hi, I had a couple of questions. So one was like, so you, in one case you said there is, can you just go back a few slides to maybe 23 or something?
This is the problem of Zoom. 23.
Yeah, where you talked of two invariant measures, nu A and nu B, and then...
Here. No, sorry. Here.
All right, yeah. So, so I was a bit confused. I mean, so you're saying if there are two invariant measures, then, but they give rise, when you take an expectation value, they give rise to the same channel invariant, the quantum
yes.
channel has
yes,
yeah.
whatever is the invariant measure, if you take the expectation of your state with respect to this invariant measure, it gives you the invariant state of your quantum channel. And if you have a unique invariant set, which is the case of the one atom measure, so whatever is the initial measure, if it is invariant, then the expectation is always the same.
Okay, but if there are two invariant measures, I don't know what you meant by that. It's not unique, is it? Like,
well, so at this stage, at this slide, what I know is that for my quantum channel phi, I have a unique invariant state, which is given by the Gibbs state. This is the result of Laurent Bruno and Claude-Alain Pillet. But I don't know if there exists a unique invariant measure. But what I can say is that if there exists two invariant measures, I can say that the expectation of my initial state with respect to nu A or nu B will give me the same invariant state.
okay.
And in fact, is much stronger. It means that if you have a process which depends only on the result of the measurement, it has the same law under nu A and under nu B. This is what I have written here. The expectation of f of zt with respect to nu A is equal to the expectation of nu B with respect to of f of zt with respect to nu B. It means that if I have two invariant measures, any process which depends only on the result of measurement have the same law under these two measures. And what I show at the end is that my quantum trajectories, which is not which depends on the initial state, in long times it will be closer and closer to a process which depends only on the result of the measurement. So it means that this is what I have written here, that I don't make the details, is that imagine that now, no, sorry, I didn't write it. No, sorry, I didn't write it. So, sorry. So you say that now, imagine that you have two invariant measures, nu A and nu B. And you want to compute the expectation of an observable of rho t with respect to nu A. In long time, this expectation will be closer to a process which depends only on result of the measurement. So it means that the expectation of nu A of f of rho t is almost equal to the expectation of nu A of f of some zt. But this expectation of nu A of f of zt is equal to the expectation of nu B of f of zt, which is also close to the expectation of nu B of f of rho t. And in this way, you can show that the expectation with respect to nu A of f of rho t is close in long time to the expectation of nu B of f of rho t. And when t goes to infinity, these two expectations are equal. So it means that nu A is equal to nu B. I don't know if I have been clear enough.
Yeah. I had another question. I mean, like maybe you already said. I mean, so you showed that there's a unique invariant measure, but like, do you have some idea what this invariant measure looks like?
Absolutely not. It's so here yes, here I know exactly what is the invariant measure. This is this. Here I know that the invariant measure is located on the Fock state, and the probability to be in the state K is given by this, which is, in fact, if you take the Gibbs state, what is the probability for the Gibbs state to be in the Fock state K? You take the scalar product, and then this gives you this quantity. So here, I know, but in general, we don't know. Even in finite dimension, we don't know unless some particular cases, we absolutely don't know. So maybe if you know a bit what is the product of random matrices, you know that the invariant measure of this product of random matrices are related to fractals. And here we have product of random matrices. So it should be related to fractals, but we absolutely don't know. We don't even know if it is absolutely continuous with respect to a reference measure. It's a very difficult question.
Thanks.
Any other questions?
Yeah, may I have some question?
Yes?
You tell at the end that there is some large deviation regime, but without a central limit theorem.
Yes.
Can you a little more why? Is there the second derivative is infinite or
Yes,
in the
something like that. Exactly. The problem is that my way of seeing the central limit theorem in this case is you want to solve, for example, what is called the Poisson equation, and the Poisson equation has no solution. So
okay.
it somehow is like you can have a large deviation principle, for example, for Cauchy sequence, and here you don't have a second moment or something like that.
Okay, perfect. Thanks.
So if there are no other questions, let's thank Clement and all the speakers of this morning session once again.
Thank you.
Abhishek, you conclude?
Yeah, hi. Raphael, you want to show yourself?
Yeah, okay. Yes. Hi, everybody.
We can't see you.
It's not important. I let you conclude, Abhishek.
Clement, can you close your the sharing?
Yeah.
Yeah. Raphael, did you join on?
Yeah, I am here.
Okay, we hear you. Okay, anyway, so thanks, Clement, for waking up very early, and also thanks, Raphael, for joining, waking up very early, I guess. And so this is the last talk in the program. So we had, I think, quite a good program. So I want to thank again all the people who are still there, so I just want to remind you, the program office will send out some feedback forms. Please please give your feedback about the program. And also what's most important is that please do remember to acknowledge if you write any paper or based on what, like your participation in this program, please make sure that you acknowledge ICTS. So again, the program office will send out emails about the format of acknowledgement, which you can use. Okay, so I hope you all have a good trip back home. Raphael, you want to say anything?
I want to tell thanks for everybody to coming here. It was very nice to have you.
Okay, bye.
Okay.
I think everyone who's left, we should give a round of applause to Abhishek for all the work that he's done in the organization, especially.
Yes.